All right, folks, looks like it's about time to get started. Thanks for joining us today. Those who are joining via Zoom, thanks for being here. This is our, I think, fourth workshop on this series of HPC workshops that we're doing this semester. So thank you for your continued participation and attendance. We really appreciate it. So last week we covered how to run your jobs on the HPC. And this week, we're going to cover managing and optimizing your job. So it's sort of a segue into the next topic. As usual, if you have any questions during the presentation, feel free to drop them in the chat and I will try to respond to them. All right, let's get into it. So here's a general outline of what we're going to be covering today. We have prerequisites and overview at the top. Then we'll talk about job management, and then we'll talk about job optimization, and you can see the subsections there. So prerequisites, we are going to be assuming during this section that you are familiar with the HPC system overall. This is the fourth installation of our lecture series, so we assume that you know how to access the HPC, how to create your account, how to, or that you know this at least a general overview of the system layout, i.e. the node types, the difference between a login node and a compute node, that you know what batch jobs are, or at least interactive jobs on open on demand. And we're going to be using some simple bash commands as well as some basic computer literacy terminology like CPU, processor, RAM, storage, etc. So if any of these things feel unfamiliar to you, we definitely recommend that you review some of our other training materials before proceeding with this workshop. But that being said, let's get into it. So yeah, if you're a new user, check out our Intro to HPC course before you start going into this topic. So our overview. So managing your workflow on HPC is a very crucial component of the research process. That is, you're running jobs, you're managing files, you're moving things around, doing lots of different types of things. So it's quite common for users to have dozens, maybe hundreds, or even thousands of jobs, maybe 1,000 jobs running simultaneously. Alternatively, you may have a small number of very highly resource-intensive jobs. So, every user's workflow can be totally different. So we're not trying to say that it has to look like this or that, but we're going to give you some very general tips to hopefully help you manage whatever workflow works the best for your particular type of research. So in this workshop, we're going to learn what available tools and best practices are for keeping track of your work, about tailoring resource requests for all job types, system commands for tracking job performance, general practices for configuring software to run more efficiently. And that's going to be the main topics that we talk about. So what is job management? We're going to clear up maybe the difference between job management and job optimization here, because we're going to kind of tackle them separately. They are certainly related, but job management is keeping track of your active jobs or completed jobs and how many resources they are utilizing. And also keeping track of how previous jobs have performed, whether they failed, whether they got killed because of an out-of-memory error, whether they completed successfully, whether they were very efficiently using the resources they were assigned, or whether they were inefficiently using the resources they were assigned, as well as awareness and adherence to best practices. So why is job management important? First of all, it helps you keep your work organized. It helps you develop a clearer understanding of how HPC works, and it helps improve your research throughput. So overall, it helps you become more productive, get more work done, get more research done. And so what is job optimization then? Job optimization is about improving the efficiency of your jobs. So requesting the optimal amount of compute resources, i.e. not too much, not too little, hitting that Goldilocks zone. It requires understanding your compute needs. So this requires testing and configuration and all these types of things. So configuring and or executing your software to use those resources most effectively. So we'll talk about that a little bit later. This is highly software dependent, but we'll give some general examples. And why is job optimization important? So first of all, it helps you to get your jobs to run faster or to scale them to be larger. So efficiently using your resources means that you're not paying effectively, using your allocation, not in terms of actual dollars, but you're not using up that allocation to have CPUs that are sitting around doing nothing, right? And then when you have that job that's more efficient, those CPUs are then freed up for additional jobs that can either be run by you or other users on the system. And then, of course, if you're using those resources more effectively, then you can get more jobs to run in a shorter amount of time or bigger jobs to run. And of course, as I mentioned, using your CPU time allocation more efficiently. If this is a problem, if you're in a group with a lot of students that has a large need for computation, you might find that you're running out of your monthly CPU time allocation. So if that's a problem, definitely looking into job optimization is a great way to get more out of that CPU time allocation. And then, of course, freeing up idle resources for other HPC users, which helps improve the overall efficiency of the HPC system, get more research done overall by the community. So there's a community aspect as well as a personal aspect to this. So job management, let's talk about how to keep track of and get information on your jobs for both current and previous jobs. So there's two main modalities for the HPC interface. And if you've been coming to our workshops in the past couple of weeks, you may see some repeated information, but we're going to mostly give that as a really basic reminder of how this stuff works and then get into the more details. So for the two main modalities, you may choose to just use one. You may use both depending on what your needs are. So we have the graphical web browser open on demand, as well as the command line interface. We talked about how to use both of these things in our system access workshop. So the basic differences are that the open on demand gives you an interactive desktop, a graphical desktop where you can click folders and move things around just as you would on a normal laptop. And then the command line interface is text only. It gives you something called an interactive terminal session. Both of these access compute nodes. One is text only, that's the terminal session. One is graphical, that's the open on demand interactive desktop. So open on demand also gives you access to graphical applications such as ANSYS or MATLAB, while the command line interface gives you access to batch jobs, both of which we've talked about previously. And then open on demand also lets you use servers such as Jupyter and RStudio. So on open on demand, there are a handful of different available tools for job management. So being able to see what jobs are running, being able to view these things and see what's going on for maybe any active sessions that you have. So when you go to the Jobs tab on Open On Demand, you'll see a button that says Active Jobs. If you click this, you'll see an interface that gives you information on all of your active jobs. And then if you go to My Interactive Sessions there, you'll be able to see your interactive desktops. So there are some limitations to using Open On Demand to manage your jobs. So there are certainly great tools for viewing and keeping track of jobs that are currently running or pending. That means jobs that have been submitted to the queue but haven't quite started yet. However, if we want to view our previous jobs or get more detailed information on those jobs, we have to use the command line because Open On Demand doesn't give information on previous jobs, or it doesn't give terribly detailed information about those currently running or pending jobs. So if we want to do more detailed job management, we want to SSH onto the HPC and use some commands on the terminal in order to get that information. And we're not going to get too crazy here. So if you've never used this before, hopefully this will remain accessible to you. However, if you are also an experienced command line user, hopefully this will give you some more information about the tools that are available to you on the system through this method of access. So SSH is a way of accessing the HPC from a terminal window. Mac and Linux, this is a built-in command. Windows, you can use an SSH client like PuTTY. So that's the logo for PuTTY there. So depending on what type of computer you're using as your personal computer, the exact way to SSH differs. So if that is something you'd like more detail on, check out our system access workshop. So let's try it. If you've never used SSH to access the system, it's not a bad idea to try it now. Hey, welcome. So basically just try to open a terminal window and to access SSH. So we will use this later, so don't worry if you can't get it to work now, but we're just going to keep moving on, and when we want to use it later, then we can maybe pause and try to do that. So just as a quick recap of batch jobs, so this is another type of job that you can run on the HPC using the terminal. So let's recap real quick. Batch jobs are a way to run code automatically without user oversight or even an active connection to the HPC. Just like all other job types, batch jobs are allocated compute resources through the task scheduler. Unlike other job types, batch jobs require a batch script that determines everything the job will do, and including the resources that the job needs, such as CPUs, etc., in advance. And the batch script is submitted using the command sbatch and then the name of your script, and then it will proceed through the queue automatically. So once you've done the sbatch command, you can log off, and that job will continue to move through the queue and then run once its turn starts. So here's an example batch script. We have a few different sections here. The shebang is that thing at the very top, the first line there. And then the second section is directives. So they all start with the pound symbol and sbatch. And there's a ton of different options. You can check out our documentation or review last week's workshop for more details on the directives that are available. But this is just sort of a minimum viable amount of directives that you see here. And then the code section at the bottom. So we're loading a module and then running some commands down there. So that's what is actually getting executed in your job. So let's look a little bit more at detailed job management using Slurm. So Slurm is the task scheduler used by our HPC as well as many other HPC systems. There are two main commands that Slurm provides to you to get more details about your jobs. There are certainly others, but these are the two ones that might be the most useful to you. So SQ gives you information on current, that is running or pending jobs. And SAccount gives you information on finished, that is completed, canceled, or failed jobs. Both have a ton of different options to get a lot of different details on your jobs. So I definitely recommend checking out the official Slurm documentation for these commands. There's a ton of options in there that will allow you to get hopefully the information that you need about your job. And I'll just say up front here that Slurm does not give efficiency information for your jobs. You'll have to use a different tool for that, but we will talk about that. So a simple example for SQ might look something like this. Your command is just going to be SQ. This is the simplest version of SQ that you can use. And the output is going to be, so this will be the header of the output. And for this particular example, which jobs, it's going to print every single currently running or pending job on the system, which might be a little overwhelming. So if you can SSH into the HPC, I definitely recommend doing so now and then typing that command. So SQ like this. So what do you see? Is the output useful? Let's do that together. I'll open up on demand. So you don't necessarily have to SSH. You can also open up a terminal through open on demand to do this. So that's what I'm going to do so that you can see my screen. Logging in. Okay, here's open on demand. If you go clusters and shell, then you get your terminal session. So here's my terminal session. I'm going to make it a little bigger. And then I'm going to type SQ. And then it's going to print out a very large list of jobs. So you can see if I scroll up, it's very hard to get particular information about any jobs that I might be running. So let's go back to the presentation. Oops. So is that output useful? Not particularly. So there are certain filters that we can apply to SQ in order to get better options. So here are just a couple of different examples, certainly not complete, but if you want to just get the top 15 lines, you can use the pipe So that's in bash, that vertical line is called a pipe. So you can pipe the output of SQ into the command called head, which returns the top number of lines that you provide to it. So in this case, I did -n15. If you wanted to do more lines, you could certainly put a higher number there or a lower number. And then same thing with tail, but instead it prints the bottom 15 lines. So that's just a good way to sort of filter the top and bottom of the output if that's what you want to do. If you want to just get a certain number of lines, you can pipe the output of SQ into a command called WC, which stands for word count. And in this case, you're going to use the -L option to count the number of lines, the output. And that will simply just tell you how many jobs are in the queue at the moment. So if I were to do that, let's give that a try just to see how many jobs are in the queue right now. So if I do SQ pipe WC-L, then I get the output 2,476. So that tells me at the moment the number of running and or pending jobs, well, maybe not and, but or pending jobs would be that number, 2,476. So that's quite a large number of jobs that are currently running on Puma. And I'll just also point out here that this command is specific to the cluster that you are actually on at the moment. So right now, this is only jobs for Puma. If I wanted to see jobs for Ocelote, I would have to switch to Ocelote and then do the same thing. And now we can see that there's a different number of jobs running on Ocelote. So these are separate. So if you don't see your job in SQ, double check what cluster you're on and make sure that you're on the one that job has been submitted to. So let's continue. And then this last option here, --user. So this would be a way to specify the user for the output of SQ. And you could either type your username or use the environment variable. So in bash, we're just adding a little bit of bash information here as well. So if you have a $sign and then a variable name in all caps, that's something called an environment variable in bash. And in this case, the environment variable user is just going to be your particular username. So you could copy and paste that in exactly as it is, and it should work to print your jobs. So just to demonstrate that and add a little bit more bash information, if I typed echo, which just means print the output of this user for me, then it prints my username. So that's a useful command to have. So if I wanted to look at my jobs, I don't have any currently running on Ocelote, but just to demonstrate here, if I did this, you see that I have no jobs. So if I did have jobs, they would appear there. You get the idea. Okay. Let's continue. And here is the output of the SQ command. I ran it a while ago, so these jobs have probably completed at this point, but this is just an example. All right, so here's a more advanced example. We'll try to run through this information one piece at a time. So the command that you're seeing at the top there is an SQ command, as you can see. So it starts with SQ. Then we're using this -O flag to specify output formatting. So if you've ever used output formatting before, this should look familiar to you. The % symbol, the number there refers to the number of spaces that you're giving that particular piece of information. And then there's a letter code that tells you what information that is. And you can look on the official Slurm documentation to get these. I definitely don't have them memorized, so I always have to refer back to the documentation to see what they are. But I've labeled them here. And then the last thing on the very right-hand side that's currently squared in that orange box is that option that we said before, but just in a slightly different format. So previously we did 2 dashes, user equals that $sign bit there. This time we're using a single dash and a lowercase u. So there's a few different ways of formatting your options in the SQ command as well as the saccount command. And I'll also point out that one unfortunate, mildly annoying thing about these two commands, SQ and saccount, is that the option formatting for both, for either command is slightly different. So something that might work for SQ might not work for saccount. So pay attention, double check the documentation when you're using these commands to get information about your jobs to make sure that the formatting style that you're using for them matches the type of command that you're using. It is unfortunate that they haven't synchronized that formatting, but that's just the way things are. So here in this particular command, let's go through each of the options and see what they are. So the first option there, that %10i, tells me the job ID. Then the next one, %12p, that gives me 12 spaces for the partition. So there you might see standard or high priority, something like this. And then name, that's going to be the %10j. So unfortunately, sometimes the letter codes don't always make perfect sense to what the output field is. So J, name, oh well. So it's always good to use that reference. That would be the name of the job, whatever name that you provided the job in your batch script, your username there, then the state of the job. So that would be something like pending or running or completing, something like this. And then time, so that would be the amount of time either that the job has been sitting in the queue or the amount of time that the job has been running for. So that's a good piece of information to have. The %6d there, that tells me the number of nodes that I'm running on. Then the number of CPUs. And then QoS there, that's a special thing that Slurm has. QoS stands for quality of service. That just refers to particular resources that are being used. In our case, that mostly refers to whether or not the job is using a GPU and what type of GPU that is. So that's probably the type of information that's going to show up there. And then lastly, the %R, that's going to give the node list if the job is running, or if the job is still pending. In parentheses, it will tell you the reason why that job is still pending. So if everything is normal and good, you'll see either priority or resources there, just meaning that the job is still in the queue and that everything is normal. You might see another reason code there, such as something like assoc group minutes left. If you see something like that, it means that you've run out of CPU hours in your allocation. And of course, there are a handful of other different reasons that might possibly show up there. So we have a few of those in our documentation, as well as Slurm's documentation has a complete list of those different options. So if you see one there and you don't understand what it means, check our documentation first. It's probably in there. And if it's not, if it's a maybe less common one, check Slurm's documentation. And if you still don't understand what it means, feel free to shoot us a message, but that information should be available to you. And then some other options, you can always filter things from the SQ command using the state flag. So if I used this exact format here, --state equals r comma pd, that refers to specifying jobs that are either running or pending. And you could also use the partition name. So if I wanted to only look at my windfall jobs, for example, I could put that there. And then there are plenty of other ways of filtering the jobs. Again, Slurm's documentation is going to have complete information on that. So that's a more advanced example with SQ, passing very particular fields of information to it to get the exact information that you want. You're not just stuck with the basic format that you see here. So there is some useful information here. So you do still see the node list and the reason, the time, the state, all of these things, right? So there is still some useful information here, but there is a way to get more information out of SQ than just this basic format here. So if you want more information, you can go check the different options that are available via the output formatting in SQ to see what options are available to you. Okay, so that's SQ. Remember that there are two of these main commands to talk about. SQ and saccount work very similarly. Again, not exactly the same, but very similarly. The thing is that they pull from slightly different databases. So the SQ command pulls from the database of... is there a question?
Okay, great.
Okay. If there's no question, then I'll continue. So what I was saying was that the SQ and SAccount commands pull from slightly different databases. So SQ pulls from the database of jobs that are in the queue or currently running. So if you know that your job is in that particular state, then you'd want to use the SQ command. If your job has completed, then it won't show up in the SQ command. You'll have to use SAccount instead. So for completed or failed jobs, they'll show up in the SAccount database because, again, two slightly different databases, two different commands, and slightly different formatting options for those commands. So we'll skip going into that in detail because now that you've seen SQ, you kind of get the general idea of how it works, and you can check the official Slurm documentation. And if there's anything that you might need help with, if there's some piece of information that you want to get from either SQ or SAccount that you're not able to get, feel free to shoot us a message, and we would be happy to help you out. So one more Slurm command. So we've talked about SQ and SAccount. This one is called scontrol. So scontrol can be used to, you guessed it, control your jobs. So first of all, you need to have your job ID. So that is important. Then you can use a command. So the format for scontrol would be scontrol, the name of the command, and then the job ID. So some common options for command include suspend. So that would be to pause a job that is currently running. To resume, again, that would be to resume a job that had been paused with suspend. To hold a job, so that would prevent a queued job from starting. So if for whatever reason you've submitted something to the queue and you don't want it to start just yet, then you can use this command. Release would release the held job. So you can see these commands sort of come in pairs. And then the show job command would provide detailed information on a job. And again, you would still have to provide the job ID afterwards. And those are just some common options. There are certainly more. Again, we're just sort of giving you this overview of these commands that do exist on the system and a general way of using them. Okay, so that's scontrol. So a handful of more job management tools. So these are, yes.
Before go on.
Sure.
That question out. I'm trying to SSH under HPC with a working trap or HPC to UArizona.edu, my net ID. However, it's failing to connect. I can connect directly from ORD though. I think there's another domain name that I should use for local machines. See, missing the net ID app.
So I'm going to type something into the chat here just to respond to that. Just so you can see it clearly. The command to SSH would look something like this. So I'll type in my username. You'll obviously have to put your own there. So that's what the command would look like. You need to type SSH and then your username at hpc.arizona.edu. So you do have to have that username there. And the format shouldn't change depending on the type of machine that you're on. But since this is an SSH question, I'm going to say if you're still having trouble by the end of this workshop, just shoot us a message and we can help you out with that later. But just for brevity, we're going to continue on with these job management tools now. So there are going to be a handful of different job management tools to help you determine how busy the overall HPC system currently is. So the nodes busy command is great. This gives you details of how busy each node is on the particular cluster that you're on, and it's a graphical output. So let me show you what that looks like. If I go to my shell here, and I type nodes busy, takes a second, and then if I scroll up here, I can see all of the different nodes. And just to show you all the way up, I am indeed on Ocelote. So these are all of the nodes on Ocelote. So you can see quite a lot of them are at 100% capacity. So The system is quite busy right now, but there are still a handful of nodes that aren't in use. So if you're wondering, perhaps you've submitted a job to the queue and it's not starting, this might be a good thing to check. So that's nodes busy. Cluster busy and system busy are also tools that you can use. Cluster busy is similar to nodes busy, but it tells you all three of the clusters at the same time. And it just gives you one metric for how busy the system is. So rather than showing you details for each of the nodes, it just shows you the percentage of capacity that's in use for that cluster as a whole.
By nodes, for example, just the GPU nodes.
I don't know if you can filter exactly, but there are the sections in there. So let me show you. If I go back over here, so you can see, if I scroll up just a little bit, this section of the output is GPU nodes. So I don't know if I can get rid of the other side. I don't think you can do that. But so here, if I go all the way up, this first section is standard nodes. Then I can scroll down and then I can see the GPU nodes. So that section, that information is still there. It does tell you what the GPU nodes are. So hopefully that gives you the information that you need. So those three commands at the top there are sort of big overviews for the system. And then if you want to look more in detail at your own jobs, here are some commands that might be useful for you. The past jobs command, you'll use the -d flag to pass a number of days. So if I want to check my jobs from the last week, I could use past jobs -d and 7, and it'll automatically detect who you are. You don't need to specify your username or anything like that. And that'll just print that out. Again, let me go ahead and demonstrate that. I'm going to use Elgato here because I know that I have jobs there. So if I go past jobs, space -d and then 7, it's going to list out a handful of jobs that I've run in the last week. And that's what the output will look like. And that's a good way to get your job IDs. So if you're like saying, oh man, I know that I've run a few jobs, I don't know what their job IDs are, and I want to get more detailed information about them, I can use past jobs to say, oh, here are the jobs from this time period, and those are their job IDs. And then I can use those as inputs to other commands, such as CEF, which is an efficiency report, as well as job history, which gives more detailed job information. So let's just take a look at both of those. We can demonstrate them real quick. So let's just use this RStudio job that I have right here. So I copied that job ID and I'm going to type it in CEF, put that job ID there, and you can see that you have all of these different metrics that can be printed out for that job. So if you want to know the efficiency of a job, such as the CPU or memory efficiency, you can see here. And as a caveat, these are sort of averages for the job. So it might not tell you the peak CPU usage. It might not tell you the peak memory usage, but it will give you sort of a general idea of how the job performed as a whole. So that's CEF. And then I can also use job history to get more information about that job. So job history won't give you efficiency information, but it will tell you all of this stuff. So which account the job was used with, the time limit, how long it actually took, when it started, when it completed, the cluster, the resources, all of these things. So as well as the working directory. So that's another thing to, that's another commonly used feature of job history. So those three commands together are pretty powerful. They let you see all of your jobs from a particular time window. You can get an efficiency report, and you can get a history report for all of the resources and other metrics for that job. All right, let's continue. So to recap the job management section, we just learned how to see current and pending jobs in the Open On Demand browser, how to SSH into the system, how to use Slurm commands such as SQ, SAccount, and SControl to view details of the running, pending, and completed jobs, and then other system commands to help with job management. So that's all for job management. Next, we're going to talk about job optimization. But before we start that, are there any questions on the section that we just covered?
Let's stop the note if you can get in there.
I can see. Thanks, Alex. All right, let's just continue on to the job optimization section. So we're going to talk about how to get the most out of your jobs and how to get the most out of your standard CPU time allocation. So why do we need to think about job optimization? You know, it's a supercomputer, right? There's a million nodes on it. Why do I need to think about job optimization? So first of all, you can get more out of your allocation. It is a finite amount. So if you find that your group is running low, it's a good thing to think about how to get more out of it. So 150,000 CPU hours per month on Puma sounds like a lot, but if you're running jobs with hundreds of CPUs for hundreds of hours, you'll hit that limit pretty quickly. And 100,000 CPU hours per month on Ocelote. So if your allocation is shared between many users, or if you tend to run out of the CPU hours, these optimization practices can help improve your research throughput. And even if you're not running into that limit, it is still good practice to try to optimize your jobs, because if your jobs are being assigned resources that aren't being used, then that's you know, a potential loss of the system. Those resources could have gone to other jobs that could have been running at the same time. So if your jobs have, or just in general, if there are jobs on the HPC that have been assigned CPUs and memory that aren't being used, that generally leads to longer wait times on the system. So we can kind of help each other out by improving our job efficiency that will make sure that we only use the resources that we really need in order to decrease the overall wait time and the overall efficiency of the system. So let's keep going. The majority of jobs optimization can be broken down into two categories. The first would be making appropriate resource requests. And the second is calling the appropriate options when running your software or configuring your software the correct way. So we'll spend most of our time on category one as it's the most generally applicable. And we'll discuss certain runtime options for certain common software, but as every software is different and has different options and needs to be called differently, it's hard to give details on how to do that for your particular situation in this presentation. But if you do have questions, if you're saying, oh, hey, I'm running this software and I want to make sure that it's you know, running more efficiently, that I'm configuring it correctly, feel free to shoot us a message and we'd be happy to take a look at your particular situation. So as a note, it is possible to further optimize your jobs by developing more efficient code, but that falls more under the umbrella of research software engineering than a typical research software user. So that generally means like cracking open the hood of your software and managing the different parallelization algorithms that might be going on underneath the hood. And if that's your speed, that's awesome, but most users aren't really going to be doing this. So that's not something that we're going to be covering in this presentation. We'll talk a little bit about that in our presentations on parallel computing that will happen next week and the following week. So next week will be the theory of parallel computing. The week after that will be parallel computing in practice. So we'll talk a little bit about that there, but because it's such a case-specific thing, we're not going to be able to give, you know, every possible detail that every user might need in every situation. So that being said, let's talk about making appropriate resource requests when submitting jobs to the HPC. So the goal here is to make sure that the ideal situation would be to use 100% of the CPU for 100% of the job's runtime and to use 100% of the memory for 100% of the job's runtime. This is in practice, not necessarily going to be possible, but the goal here is just to get as close as we can without drastically overshooting the resources that we have. And of course, if we underestimate the resources that we have, then that can lead to job failure. So basically, there's two questions that we need to answer when making these resource requests. First of all, what resources are available? And second, how many or what resources do you need to run your job? So we're going to cover the hardware in just a moment here. So we'll cover what hardware is available on the 3 different clusters. We did mention this last week, so if you tuned in last week, that might sound familiar to you. And second, how many do you need to run your job? So this is the harder question. The main answer to this is trial and error, or to use scaling tests. So we'll talk about these in more detail just now. So first of all, how do I submit a resource request? If you're on Open On Demand, you're going to use something called the Job Composer, which is a form that you'll need to fill out in Open On Demand, where you select things such as the amount of time that you want to assign to your job, the number of cores, as well as the memory per core. So these are all options that we'll talk about. When using a batch job, the resource request is going to look a little bit different, but effectively it's the same type of thing, just formatted a little differently. So you're going to need to use the batch directives section of your batch script in order to request the resources that you want. So in this example here, you can see that directive section on the screen. I'm requesting 1 node. I'm requesting 1 CPU for 1 minute. So this job is basically just a test job. You might, in practice, need to request more CPUs for a larger amount of time. You may even be doing multi-node jobs in which you're requesting multiple nodes and a large number of cores per node for a long time. So, this is going to scale with your compute needs. So memory per CPU will be set to a default value on the standard node if it's not specified. And see our documentation. This website is slightly outdated. It would be hpcdocs.hpc.arizona.edu, just as a note if that doesn't work. And we do have a full section on batch directives in our running jobs section of that documentation. So please check that out. There's a lot of great information in there. So we have 3 clusters on the HPC Center: the Puma, there's Ocelote, and Elgato. Each cluster is built from different hardware, so resource requests in Slurm will need to be tailored to which particular cluster you're submitting to. If I write a resource request for Puma, it might look a little bit different than the resource request that I'm submitting to Ocelote. So that's important to keep in mind. So lots of numbers incoming in the next couple of slides. You don't need to memorize these. They are in the documentation. But, it may be that you do end up memorizing them after familiarizing yourself with them, but at least right now, don't feel like you have to. So here is the hardware that's available on Puma, and I've highlighted the memory per CPU row because that's going to be one that is very important when you're submitting either batch jobs or Open On Demand jobs, because on Open On Demand now we have a drop-down menu, but previously you could enter any value there. So these are fixed values. They're not sliding scales. Your total memory is going to be equal to the number of CPUs you get assigned times the memory per CPU. So if I am running a job on Puma and I'm using 10 CPUs on a standard node, I'm going to have 50 gigabytes of memory or RAM, right? And that's again, not a sliding scale. If I'm running a job and I want to specify the total memory, it's always good to make sure that the total memory I specify is equal to the number of CPUs times the memory per node on the type of node that you're using. So there's many different ways of constructing these resource requests, and it's important to make sure that all of the numbers match up. They're not arbitrary numbers. If you put any old number in there, you might end up with either jobs that get canceled or fail for whatever reason, or they might just behave differently than you expect them to. So for example, if I'm submitting a job to a standard node on Puma, and let's say I want a lot of memory for this job. Let's say I want 100 gigabytes of RAM for that job. That is certainly possible to achieve on Puma, but let's say, maybe it's a very memory intensive job, but not a very CPU intensive job. Let's say I'm just thinking and I'm not aware of these restrictions, right? And I say, oh, maybe I want one CPU with 100 gigabytes of memory. Well, if I submit the total memory of 100 gigabytes to the scheduler, well, it's going to say, well, sure, you want one CPU, but you also want 100 gigabytes of RAM. So what I'm going to do is assign you actually 20 CPUs in order to match that memory request that you made. So in your mind, you might be thinking, oh, well, if my job runs for 10 hours, then I'm only using 10 CPU hours of my allocation, when in reality, I'm using that 20 CPUs that gets assigned because I asked for 100 gigabytes. And again, if it runs for 10 hours, 20 times 10, that's 200 CPU hours. So just thinking about managing that allocation, especially if you're in a group that tends to run that down, it's important to just be aware of this. So basically, this is just to point out that it's important to make sure your resource requests match the way that the scheduler actually functions in order to avoid any unexpected behavior or in order to avoid any potential errors that might show up. So that's that example. Here's the hardware information for Puma, 5 gigabytes of memory per CPU on a standard node. Going to Ocelote, we have different values here. So a standard node, you have 6 gigabytes. So this is why you would need to make sure to tailor your resource request to the cluster that you're submitting to. If I have a job that I submitted on Puma and I want to move that over to Ocelote, I have to redo my memory request in order to make sure that it matches the values for Ocelote. And then same thing for Elgato, slightly different values for these here. And one thing also to be aware of is that there are different numbers of CPUs per node. So if I'm running a program that does not invoke multi-node parallelism, which if you know what that is, you're probably using that. If you don't know what that is, you're probably not using that. So if I'm running a job on Puma and I'm using 94 CPUs, I don't need multi-node parallelism because that's the number of nodes on, or sorry, the number of CPUs on one node. However, if I port that resource request over to Ocelote and I don't change the number of CPUs, now suddenly I'm requesting a multi-node job. And if I haven't configured my software to use multiple nodes, then those extra nodes that get requested aren't going to be used by that job, and they're just going to sit idle. And you're going to be paying in your allocation for resources that you're not actually using in your job, and then those resources are also not available to other users. So many things to be aware of here. Okay. So we talked about the common fields in your resource request, such as the number of CPUs, the number of nodes, the memory that you'll need, so that, in other words, RAM, and also GPUs. So that's not something we've talked about yet, but that is another resource that exists on the HPC that you're able to use. And again, if you're going to be requesting a GPU, make sure your software knows how to use the GPU. So we need to know what our options are when inputting these fields. So this is something that I had mentioned right now. So the total memory is going to be equal to the memory per CPU times the number of CPUs. Again, it's not an arbitrary value. And here we're talking about RAM, not disk space. Oops. So again, know the value of RAM per CPU. If you're going to use the total memory flag, make sure to just do the quick, back of the napkin calculation, make sure that it equals the number of CPUs times the memory per CPU, and only use the correct values for that cluster for memory per CPU. So, all right, we're going to talk about optimizing your resource requests now that we have covered the hardware and the options that are available to you. And I just want to mention, again, if there's any questions, feel free to drop them in the chat. So now that we know what our options are for requesting compute hardware, how do we know what the best configuration will be for our particular job? The answer is pretty much testing, trial and error, scaling tests. Unfortunately, there's not some mathematical equation that I can put my code into and then it will spit out the exact hardware configuration that will run my job the best possible way. Unfortunately, that doesn't exist, so we'll have to rely on good old trial and error. here's a little flow chart that we made to help guide that testing process. So first of all, you'll need to determine what job you're going to run. That's up to you. And based on previous experience running similar jobs, or based on maybe what your PI suggests or what other group members suggest for you to run, make an initial guess for your resource. And if this isn't perfect, that's totally fine. That's why we're going through this iterative process here. So first you'll run the job. If the job fails, you'll need to check out the error message. So the error message might say something, it might say something completely cryptic that you can't interpret. In which case, go to Google, go to Stack Exchange, and if you still can't figure it out, let us know, and we'd be happy to take a look. If it's something like out of memory, well, that's going to tell you that you need to increase the amount of memory of your job. So there's a lot of different. The thing with these certain categories here is that there's so much variation in them that it's hard to give exactly what you should do for any particular case, because there's so many possible different ones. But generally speaking, always read those error messages. See what information you can get out of those error messages. Sometimes they're cryptic and indecipherable. Other times there is genuinely very useful information in those error messages. So that's in the case that the job fails. In the case that the job is running too slow, you say, oh, well, maybe, I ran this job on my MacBook and it finished in 10 minutes, and now I'm running it on the HPC and it's taking an hour. This is possible. Double check your software configuration, double check how you're calling the resources that you need. Check your software packages. There's a lot of different things that can cause this. One possible option would just simply be to increase the number of CPUs. Again, increasing the number of CPUs is only going to improve the speed of your job if your job is configured to use those CPUs. So if you have a program such as Python, which is natively serial, meaning that it only runs on one CPU, you'll need to configure that, use a library like multiprocessing in order to make use of multiple CPUs. So increasing the CPUs only improves the speed of a run if that software knows how to use those CPUs. So that's something we'll talk more in detail about in the parallel workshops that are upcoming. And then if you have a successful run, if the code works as expected and completes, it's always good to double check the efficiency report. Maybe, the CEF command that we talked about a few minutes ago. So checking that efficiency report, maybe you open it up and boom, you got 100% efficiency. That's great. Otherwise, if there's something limiting the efficiency of your job, then you can go back and update your resource request. Maybe you can scale back the resource request if the job wasn't very efficient, in order to effectively use that allocation more effectively, free up those resources for other users, right? So there's this two-way street of sometimes you need to increase the amount of resources that you have in order to get the job to run better. Sometimes you need to decrease the number of resources that you're requesting in order to get the job to become more efficient. So a few additional notes on testing. So job failures can result from insufficient memory or numerous other factors. It's always good to save output logs from your jobs. That's something that you can specify in the batch directives. So I always make sure to save the output log as well as the error log, and check those once the job has finished. Even if it's been a successful run, it's not a bad idea to just quickly glance over those pieces of information. So again, if increasing the number of CPUs does not decrease the time to completion, then your job is not CPU limited, or it is not using those CPUs effectively, and it's good to reduce the number of requested CPUs. And you may need to decrease the number of CPUs requested for a successful run in order to obtain an optimal value, right? Like if I'm requesting a full node on Puma, 94 CPUs, and I'm look at my CEF report and it's only 10% efficient, especially if both the memory and the CPU are about the same, then that tells me that I can probably get away with reducing the number of CPUs that I'm requesting.
Ethan,
Yes.
in the chat, what information in the efficiency report is important to consider? What does that feedback help you change?
That's a great question. Let's take a look at an example of the efficiency report. So we just ran Ceph a few minutes ago, so I'll just pull this up. So this is not an example of don't worry too much about the exact numbers here, but we're gonna just take a look at the fields. So first of all, cores, that tells me the number of CPUs that this job ran on. In this case, there's just one. This tells me the CPU utilized was only for 14 seconds of this job. This was just a testing job that I ran, so it wasn't really using the CPU. And you can see here, the job ran for about 1 hour, and the CPU efficiency is very, very low here, so 0.39%. Most jobs that are actually running some piece of code are going to be at least a little bit higher than that. This, again, was just a testing job, so not a great example in terms of real numbers, but pay attention to CPU efficiency there. So that CPU efficiency is going to tell you an average metric of the CPU usage of that job over the course of its runtime. So you can kind of imagine a graph of like little spikes that are happening as your job is running. So it's not going to tell you the peak. It's not going to tell you the minimum. It's just going to give you a very big overview, average number of, or average fraction of the CPU that's being utilized during that runtime. And then memory also. So I think one thing to point out is that if a job is CPU limited, it might not necessarily fail. If it has too few CPUs, it might just take too long. And too long means, that's subjective to you as a user. But if a job is memory limited, then it can fail. So if a job simply does not have enough memory to load in all of the data that it needs to process, then it'll get canceled and it won't proceed. So the memory efficiency is another important thing to be aware of. So this tells me the memory utilized right here. That's the actual value of the memory that was on average used by the job. Again, not reporting peaks here. So it might be possible that at some point during the job's runtime, it used a higher amount of memory, but using this average metric is still a good piece of insight that you have as to your job's usage. So if your job failed and you pull up this memory or you pull up this efficiency report and you see the memory efficiency was 100%, well, that might tell you, well, first of all, it is good that you're using all of that memory, but it might be the case that you need to increase the number of CPUs assigned to that job to increase the amount of memory. Because remember, as we talked about previously, CPUs and memory are linked. So hopefully that gives you some insight as to how to read those reports. And we're getting near the end here, so let's keep going. So we went through that. So we just talked about the efficiency reporting tools. We've talked about job history that gives other job details. There is an additional online tool called XDMod. So if you go to metrics.hpc.arizona.edu and log in, you'll see a graphical interface where you can go through and try to get some information. I'll give you a warning, the graphical information or the graphical interface is rather dense and it's a little bit difficult to get the information that you want from there, but continue poking around. Sometimes you'll be able to find something useful. So it's a very powerful tool. It's just, takes a little bit of getting used to. So I'll just preface that. Some more efficiency reporting tools, caveat with Ceph. So we just talked about this, reporting the average CPU and memory utilization. So I always like to picture a graph like the one that you see here, where there's peaks and troughs. Unfortunately, we don't actually have that information, I don't think. So just be aware that we have these average metrics, but not super detailed time series usage metrics. Again, always check the logs, read the error messages, see what those are telling you. Here's a screenshot of something from XDMod. This would be the CPU hours used by different departments in the university. So this might not be the exact metric that you're looking for, but there are plenty of different options available in that interface. So let's talk briefly about configuring your software for optimal performance. And this will be basically the last thing that we talked about, and I'll let you guys go in just a moment.
Yeah, right.
So with so many different softwares used on the HPC, we can't cover all of the different possible use cases. So check with the developers, if you're using some software from GitHub or, whatever it might be, they might have documentation or a manual or a guide on how to configure their software, how to invoke parallelization for multi-CPU or multi-node type jobs. An important note is that your software may not automatically detect the number of CPUs that you provided in your resource request. So if your software is natively parallel, like I mentioned Python is, then by default, it will only use one CPU, even if I'm requesting 10, 15, 20, whatever number of CPUs in my resource request. So important to be aware of there. Some software is natively serial. You may have to specifically configure that software to use those CPUs. So here's a quick example of software configuration. Let's say there's a Python script that you found on GitHub to perform your analysis. Let's say, for example, it has already been written using the multiprocessing library. So thank you, developer. They've already gone through and included that in there. Now you want to use the script using 16 processors on Puma. So first of all, what should the batch directives be to request these processors? What should the line of code to execute this program look like? So you don't have to do this right now just because we're low on time. Let's go ahead and look at what we should do. So the batch directives. So first of all, we'll need to, because it's a single node job, we'll need to use these two batch directives in order to request 16 CPUs. So there's not just a batch directive that says CPUs. So we have this particular configuration for a single node job. So you want to specify n tasks equals 1. That is important to specify. And you'll also want to specify CPUs per task equals 16. And how about the line of code to execute that program? So normally, you would just run Python 3 myscript.py in order to execute that program. But when we're using multiple processors, when we want to invoke that multiprocessing library, we will need to make a call that looks more like this, where we're invoking MPI run and a number of processors equals 16 in order to get that Python script to utilize that those CPUs. So the way that you invoke that call of the script is important as well. So just requesting the number of CPUs and then saying Python my script, that might not actually utilize the CPUs that you've requested. So important to note there. Exactly what I just said. Okay, let's recap job optimization. First of all, why do we optimize our jobs? To first of all use our allocations more effectively, as well as to allow unused resources to be available to other users, other jobs. Right? How do we optimize our jobs? Well, first of all, testing. We want to make an initial guess and then revise based on runtime and efficiency metrics. Configuration, we want to make sure to call the right batch directives and command line options when running your code. And that's it for today. Thank you so much for listening. Let me know if you have any questions. I'll be happy to answer them in the next few minutes. And if you think of anything later on, feel free to send us a ticket on ServiceNow or drop into our office hours. So thank you so much.